thank you for introducing me, and thank you for the invitation. Since we're talking now about archiving, I won't talk so much about computer tomography as a method. I will try to present you some basic features you need to know about computer tomography and the technical parameters we want to archive in our database. Most of the data I'm showing is coming from our research project musicology, which is a 3 years project funded by the Deutsche Forschungsgemeinschaft, the German Research Association, and it's a collaboration of the museum I'm working in, the Germanisches Nationalmuseum, and the Fraunhofer Institute in Fürth, the Development Center for X-ray Technology. And we have a couple of co-proposers, for example, the Musical Instrument Museum in Berlin, the Musical Instrument Museum in Leipzig, and the Ethnological Museum in Berlin, where I will show some pictures so we can see some ethnological instruments. And we have also some international project partners. Our goal was to describe technical parameters for 3D CT imaging for various materials. Why musical instruments? Musical instruments are interesting because they exist in every size and in every possible material for cultural objects. So we have metal instruments, we have wooden instruments, we have mixed materials, and this is a challenge for X-ray technology. And so they can be used as a model for other objects or for every other object, and every CT technologist is happy to scan a musical instrument and not an engine or some aluminium parts. So our goal was also to describe open formats for long-term archiving and the metadata management, defining some minimum resolutions you need for several scientific issues or possible scientific issues, and the integration into open access databases was also a big point in our project. And at the end there will be a standard paper which collects all the experience of the scanning of 105 instruments and is a description of the optimized parameters we were developing. So it's not a technical standard in terms of an ISO standard, it's more a guideline. If someone has an object made of this or that material, how can I scan it and how can I archive the metadata? X-ray technology is used for several purposes. Since it was invented by Röntgen, these are two very, very early or first X-ray images, and you can see two main purposes. The one is medical diagnostic, and the other one is non-destructive testing, and this is what we are doing. Here you can see the ring of the hand of Röntgen's wife, and maybe you could see if the finger is broken. But here, what Röntgen did while scanning his hunting rifle, he wrote down what he was seeing. He sees, here are the bullets, and here is some powder or whatever. So this is what we're doing. We're making an X-ray image, and then we're describing what we're seeing. But these pictures are interesting, but not enough for us. We want to have 3D information. Here we have only 2D information, and we don't want to describe only what we see. We want to archive all the parameters we have. We would say, okay, which kind of paper would we use? Which kind of film? Which kind of current? Which kind of energy? And all the parameters that belong to one scan. This is the first CT scanner, which was invented by Godfrey Hounsfield. and which was actually made for a 3D imaging of the head for see defects in the brain. And this is the medical purpose, of course, and this is a modern industrial CT scanner. We have the X-ray source here, we have a turntable here, and this is the detector, and we can adjust the whole machine, while this machine is only is optimized for human bodies. So in there, in this tube, there's a detector and the X-ray source rotating around the body, while the object we want to study is placed on a turntable in the industrial machine, and the object turns. Why do we use industrial CT? Because the quality is much better and we can adjust it to our purposes. You can see a medical scanning here. I had to interchange the industrial, yeah, you get it. So if you want to see the connection of this vial, the viola pomposa, you can see in the medical picture that there is something, but you don't know exactly what it is. And here you can see the structure. If you look at this picture, you can see, is this maybe glue here, this, or is it broken? In this picture, you can clearly see that there is something broken and someone glued it again. So we have a lot more information in the industrial pictures and a higher quality. The spatial resolution we are talking about, here we have a voxel size of 400 microns, and voxel size means the size of one 3D pixel, and here we have a voxel size of around 100 microns. So this is the range where we can use the pictures for our studies. If we now put the instrument in the CT facility, we have a lot of technical parameters. We have the current of the X-ray source. We have some properties of the X-ray source. We have a detector with a size of pixels, an amount of pixels. We can take a number of single images. So usually we take like 1,600 up to 3,800 single images per rotation. We can choose a different measurement method. So for example, we can rotate the instrument while we are scanning and going up and down with the detector, or we leave the detector at one position, rotate 360 degrees, and then move the detector. So this is, the one is called helix measurement, the other one is a static measurement. So, and at the end we can use we have to reconstruct all these pictures. We have 1,600 pictures, and we have to reconstruct them to a 3D data set, and there we can use different algorithms. So there are a lot of technical parameters in this scan, but we have also a lot of object parameters. It depends on the material of the object. The density can be low and high. It can be metal or wood. It can be a small instrument. It can be a big instrument. It can be a thick instrument and a very thin instrument. And it can be a very easy geometry, or it can be very complicated, where you have thick and thin parts together. So all these object parameters and the technical parameters determine at the end the quality of the scan. So, and at the end all the other parameters like scan time, scan method, resolution, and at the end also the possibility what kind of issues I can answer, or what kind of questions I can answer I had before. Or if I can use it for dendrochronological dating, or like we heard yesterday, or if I can use it for 3D printing in a good way or not. So the violin is a very easy instrument. It's made of wood. It's not too big, so we can make good pictures with this instrument. So if we use a helix method, which is a very good method to avoid artifacts, then we can get a resolution like 87 microns. This is very good. The dataset will be something like 43 gigabytes. This is a bit hard to handle with a usual computer, but with a workstation it's possible. And you can use the quality of the pictures for dendrochronological dating and wood analysis. You can even see that the wood of these parts here in the violin are different. So you can have a lot of information about the instrument. Similar objects would be something like a sheng, a mouth organ, where you can see structural details, you can see how the air flows, and maybe analyze if there's a shock wave when you blow in, I don't know. Yeah. Or this sarangi, where you can see also the structure of the instrument, and also some distortion or the conservational status of the instrument and stuff like that, if you're interested in. And what is also in this kind of low density materials is bone or ivory. It's a bit more dense than wood, but still it works with a very low energy. And here you can see that this drum is made of two skulls, and you can see how they cut. You can separate the different skulls and how they cut the holes in it, and how they made the connection. And you can even see separate the textile material and maybe judge how often it was wrapped, or I don't know what you're interested in. Yeah. A more complicated instrument would be something like this, a double horn, which has a very high density and a complicated geometry. An important part is this, because there we have a lot of material and we have to irradiate like 5 centimeters of brass. And to optimize these parameters, we have to think how we can scan it best. And in this case, we would need a very high energy to irradiate the material. And in this case, we did a simulation. So we asked the computer to tell us what is the best position on the turntable. And at the end, he told us to put it in a 45-degree angle on the turntable. Then we would have the smallest distance of irradiation on the object. And these are all parameters I'm talking now about we collect during the scan. So the positioning and how we calculated the position and all this. At the end, the result was quite good. The crucial part, we can see the structure, and yeah, we can judge whatever someone wants to judge in the valves of a double horn. Similar objects could be something like this whistling pot, where you can see that we have already some problems of irradiation, because here the images, the grayscale is not very clear. So this is what we call artifacts. And if we would like to use it, for example, for 3D printing, we would have a problem with this area. But still, we can see what's going on and how the air flows. And this is a piece of a gamelan orchestra like we heard yesterday. And here you can have not so much material information. The grayscale is not always the same color. You have brighter parts and darker parts. This is called a hardening effect, so beam hardening. And there, if someone wants to know about the production, maybe he has a problem here. So he he would maybe be unsatisfied with the result. And I will tell you why. The problem is that the irradiation of X-rays are determined by the Lambert-Beer law. So if we look at here, this is the intensity behind the object, and I0 is the intensity in front of the object, and then there comes this exponential function where mu plays an important role, and mu is the attenuation coefficient. So, and the attenuation coefficient is depending on the material and the energy. D in the formula is the thickness of the material. So the X-ray interacts with the electrons of the atoms, and the more electrons you have, the more complicated it is to irradiate. So you can see that the elements wood, for example, is made of, like carbon and oxygen, and all this is very easy to irradiate, while the iron and copper and gold are problematic. Maybe you would like to use neutron radiography, which works like that. You have a spallation source where you separate protons of hydrogen and accelerate them, shoot them on a target block made of lead, and out of the lead comes the neutron, and you shoot it on an instrument like that. So the setting is almost the same. You have a detector, you have the source here where the neutrons come out, and you have the instrument in between, and you have also Lambert-Beer's law, but in this case, the neutrons are interacting with the core of the atom and not with the shell. So the rules are a bit different, and so hydrogen is a bit problematic. So water could be a problem in an object, but iron and copper are very good to irradiate. So if you compare the methods, for example, for a while, then you can see that the X-ray CT has a much better quality in scanning wood, while the neutron, you can see the same hardening effects we've seen before in the gamelan part, in the gong. And, but sometimes you have a better contrast. So there's also some advantages, but if you use it for brass instruments, you have these hardening effects in the X-ray CT, and while you can see in the neutron CT, very good the structure of the metal, and you can judge, or you can have a lot of information about the production process. So whatever you make, which technique you use, it doesn't matter. You have always the same workflow, and this is what we want to document. So we have an object, and the object has some properties, its size, material, and so on. And you have the scan, where you have also some technical parameters, and at the end you have the reconstruction, and where you have also some parameters, and you can judge the picture you see. In a diagram, you can realize it like that. So you have the object with the X-ray relevant features like metal, wood, and so on. You have a scientific issue. You have conservational requirements. Maybe you say, the humidity has to be 50%, and so on. And all these information come into the measurement. So the measurement can take place when all this information is collected, and then the technical parameters can be set. So then the technician says, okay, we choose this energy, or we have to find a way because the instrument cannot be put in a tilted position because of conservational reasons, so we have to find a different way to measure it, for example. And then at the end you have the algorithms of action. In our workflow, we give every step of this workflow an identifier. The object is identified by the owner and the inventory number. The inventory number is a very clear identifier, and we use the codes of the ICOM SimSim sigla, where every musical instrument collection has a numeral code, or here with these letters. D is for Germany, Deutschland, N for Nuremberg, G and M is the Germanisches Nationalmuseum, and then the inventory number. So the measurement takes place at a date, at some institute, and gets a serial number. So the act of the measurement is identified in these numbers, and at the end there's a reconstruction with a reconstruction method, and this is also identified by R and a serial number. And at the end we get this this name, which is used during the whole process of scanning, and at the end also for the data set. For the data set, we use DICOM as a file format. DICOM is the medical standard, so we can be sure that at least 30 years this file will be read, will be able to be read. And after that, we don't know, but yeah, we can kind of rely on that. So there are different possibilities. We can have a scan of an object where we just have one reconstruction. We can scan an object twice and do one reconstruction of 2 scans, so we have to combine also these identifiers, and we can scan an object and make different reconstructions of it, so and much more. In our database, it looks like that. We collect all the object parameters. Then we have here the technical parameters identified or named with these identifiers, and at the end, the reconstruction parameters. We use a database called ISCEA, which is an abbreviation for wissenschaftliche Infrastruktur, scientific infrastructure, and all our fields are connected with semantically collected, and behind that is a huge ontology where you can describe the whole world and also CT scans. So who wants to use this database? We thought about scientists could use it, maybe CT scanning specialists, and maybe musicologists or people who are interested in musical instruments. In the future, it will look maybe something like that. So we are just planning to build the homepage, and when you enter the homepage, you can search the objects by for example, all the 105 objects we scanned, and maybe you will end up choosing the Sheng and because you're interested in Chinese mouth organs, or you can search for the different materials. We implemented a material tree for describing all the instruments and all the materials. So if someone is interested in all the materials made of wood, then he will find all the materials that are named with wood and or paper or whatever. And at the end, he will be at some site where all the meta information is presented, and this is the clue, also a viewer, which shows the actual instrument, and this is a viewer developed by the Fraunhofer Institute, and I want to show you. Wie geht das jetzt? Kannst du mir gerade helfen? Ich möchte, dass man das sieht.
Das ist ein zweiter Monitor, ne? Achso, das ist dann nochmal kleiner. Schieb's mal rüber. Rüberschieben, andere Seite.
Es kommt. Ah. So this is this is the viewer the Fraunhofer Institute developed. I'm sorry, I can't see it on my computer, so I have to just guess. So here you can handle the data set, and this viewer, it works like Google Maps. So for 3D data, you only load what you actually are looking at. So the big data sets can be seen, like this has something like 60 gigabytes, and I can move through the object and see the details in the quality. I can also adjust when I tell him I have such graphic memory, and if I tell him if I had more, I could see a better quality. And this is not comparable to actual software where I can work with the data set, but at least I can have an overview of what the data set is possible to show me. And I can see the 3D model of it, and I can move it and turn it around and see all the details. So this is a very good approach we have in our database, and it's the first thing like that in the world. So it's very unique. Now I want to show you one animation of one of the instruments we scanned. It's a Pleyel grand piano. It's the first scan of a grand piano, of an entire grand piano, and it's made by Pleyel. So it's one of the following. Where I can start this now? It used to work before, I'm sorry. One of the later models, like the Pleyel grand piano, the musician yesterday was talking about, which was presented by Napoleon to the Persian king. Kannst du noch mal helfen? Kann ich irgendwie... Ja, das
der läuft auch da nicht.
Ja, der lief aber vorhin. Ah, okay. But that was basically it. So if you have questions, you can of course ask.